Hey students, this is Mr. Bob, and in this video, I'm going to walk through two example problems where you have to apply the ideal gas law and molarity ideas to solve the problems. So here, the essential question is how can we apply the constants of molarity and ideal gases to analyze situations? So here we go. Sample problem 1 says, a sample of an ideal gas is trapped in a container with pressure P, temperature T, and volume V. If the volume is doubled and the temperature drops to 1/3 of its original value, what is the new pressure in the container? Okay, so interesting here is that they don't give you actual values for the pressure, temperature, volume. They just give you comparative values. And so this is where it's really helpful, as always, to use dgas. Okay, and in the drawing here, we can just quickly say that this is the initial. So we have P1, T1, V1. Okay, and then the volume is doubled, so I'm not going to draw it to scale, but we have, over here we have V2 equals 2V1. And the temperature, T2, is 1/3 T1. Okay? And the question is, what does P2 equal? So notice actually in this scenario, what I've done is I've given the drawing. In doing the drawing, I've also done the givens and the unknown. Okay, so how do we solve this? So this is where the useful form of the ideal gas law comes into play here. And so let me just kind of go with a different color here. I'll go with blue. Notice the original ideal gas law says this, right? But because we have a closed system, okay, then we know that the number of moles isn't changing. By the way, the fact you know that it's a closed system is because it's trapped, okay? That's kind of a word that you want to home in on. Contained, trapped, those sorts of words kind of suggest to you, tip you off that it's an ideal. It's a closed system. So we're going to use the scenario or the form of the ideal gas law that I talked about in the last video, where P1, V1, T1 equals P2, V2, T2. Okay? So what are we solving for? We need to know what P2 is. So let's solve this equation for P2. To do that, we're going to have to multiply both sides by T2 over V2 to get rid of it on that side and bring that over here. Can I squeeze it in there? Yes. Okay, so this gets rid of that. That gets rid of that. And I'm going to rewrite it. Let me go back here. P2 equals P1 V1 T2 over V2 T1. Okay? But now we can substitute in, right? Because we know by looking over here that T2 is 1/3 T1 and V2 is 2V1, right? So I can basically substitute that in for here and here. So let's do that. So the new pressure is going to be P1 V1. T2 is 1/3 T1. V2 is 2V1 times T1. Okay, now we can do a whole bunch of canceling. This is fun. T1s cancel, V1s cancel, and 1/3 divided by 2 becomes 1/6, right? So we end up with the result that the new pressure is 1/6 the original pressure, which is what the problem was asking us to solve. What is the new pressure in the container? Because they give you the original pressure as being P. So actually, to be very exact, I could say this is 1/6 times P, which was the original pressure. That would be your answer. Okay, let's move on to question 2. Question 2 is a little bit more challenging, a little different, I should say. It's more calculator. The air in a kitchen has a pressure of 1.0 times 10 to the 5th pascals and a temperature of 22 degrees Celsius. A fridge of internal volume 0.36 meters cubed is installed in the kitchen. With the door open, the air in the refrigerator is initially at the same temperature and pressure as the air in the kitchen. Immediately after the door is closed, calculate the number of molecules of air in the refrigerator. Okay, so again, let's do a little drawing here. I don't know how long I'm going to draw a fridge, but we'll give it a shot. Okay, there's a fridge. There's the door. Okay, you can kind of get the idea, right? And what we can say over here is that P equals 1.0 times 10 to the 5th pascal. So I'm doing my givens now. The T is 22 degrees Celsius. The volume inside the fridge is 0.36 meters cubed. Okay, with the door open, the air in the refrigerator is initially at the same temperature and pressure as the air in the kitchen immediately after the door is closed. So number of molecules. I can't get number of molecules directly from the ideal gas law, but I can get number of moles, and then I can use the relationship between moles and molecules to get the number of molecules. So these are my givens. This is my drawing. My unknown is basically N, capital N, remember? Okay, so step one is going to be find lowercase n, meaning the number of moles, using PV equals nRT. So let's go ahead and solve as we always do. Solve for the variable we're trying to solve. So n equals PV over RT. Now let's plug in. Let's be careful here. Let's always make sure we're using SI units. So pascals is the SI unit. So this is 1.0 times 10 to the 5th pascals. Volume meters cubed is the SI unit, so 0.36 meters cubed. By the way, sometimes they'll give it to you in liters, and if they do, they should give you a conversion between liters and meters somewhere in the problem, but a lot of students sometimes miss that. R is the universal gas constant, 8.31. And then T, temperature. This is the number one error that students make. Oftentimes I'll see students put in 22 degrees Celsius and go on their merry way. No, don't do that. That is no bueno, okay? And I'm going to erase that because, actually, I could do it this way, can I? Yes, beautiful. Because we have to do it in Kelvin. So a quick little, remember temperature in Kelvin equals temperature in Celsius plus 273. So that's going to be 22 plus 273, which is 295. So what I would write in there is 295 Kelvin. So the number of moles, if you do this in your calculator, 1 times 10 to the 5th times 0.36 meters cubed divided by 8.31 divided by 295. I get 14.7 moles. By the way, since this is an intermediate answer, I'm going to carry more sig figs than I can in the final answer, just to keep the accuracy as best I can. All right, so how do we go from there to getting the number of molecules? Well, remember that the number of molecules is equal to the number of moles divided by Avogadro's constant. Okay, so what I'm going to do here is I'm going to say, I'm sorry, I got that wrong. Hold on. Let's rewrite that equation. The number of moles equals the number of molecules divided by Avogadro's constant. Okay, so to solve that, to get the number of molecules, I take the number of moles multiplied by Avogadro's constant. So that's 14.7 moles times 6.02 times 10 to the 23rd molecules per mole. So when you do that in the calculator, you get an answer. And if I rounded to the appropriate number of sig figs, it would be 2 sig figs. So it would be 8.8 times 10 to the 24th molecules. Okay. By the way, the Avogadro's constant, remember, is one of those constants you would get given to you as part of the problem. By the way, this is a past IB problem. This was an IB question, I think, from 2019. Part of a question, I should say. There were other parts to it. So there you go. You have 2 sample problems. And hopefully they're helpful to you. And this is the end of this video. Thanks.